So hello everyone, my name is Boris Duché. I'm a product manager from IDS, Industrial Camera Manufacturer. Our booth is just there, you cannot miss us. So you may notice that I have a French accent. I'm sorry for that. You will have to deal with it for at least 20 minutes. So the topic of today is which 3D imaging technology is right for you. You have plenty of ways to achieve 3D imaging in a vision system. 20 minutes is not enough to talk in depth about all of these technologies. So I will focus on two main technologies. One is active stereo vision imaging, and the second one is time-of-flight imaging. Okay? So before we start talking about 3D imaging, we have to talk about 2D imaging. So I will go briefly through a recap. How does a 2D camera work? So in a conventional 2D imaging system, you will have a light source, you will have a scene, and you will have a sensor. The light beams emitted by the light source will reflect to the scene and will, hopefully, for some of them, reach the sensor plane. They will cross in an optical point that is within the lens, that is called the optical center, and they will create a flip-down image at the sensor level. And then the electronics of the camera or the driver of the camera will revert the image so that you have an image in the right direction. So that is the base principle of a conventional 2D camera. That's how IDS cameras work. That's how Teledyne cameras work. That's how your iPhone camera works. It's more or less the same for everyone. The base principle. When you take a look at a 2D image, so this is in that case a monochrome 2D image. It's a matrix of pixels. With high-end sensors, you have a lot of pixels. With low-end sensors, you have not so many pixels. And each pixel is typically encoded in 8 bits. It can be more, but most of the time, when you talk about your phone, for example, it's 8 bits per pixel because this screen or this video projector is only capable to restitute 8 bits per pixel. So that's one information for one pixel. The higher the value, the brighter the pixel. Okay? So when I look at a bright pixel, the value is high. When I look at a dark pixel, the value is low. That is the base principle of a monochrome sensor. Typically encoded in 8 bits, yet when you work with an IDS camera or with a conventional industrial camera, you can usually switch from 8, 10, sometimes 12 bits. And the more bits you have to encode a single pixel, the higher the dynamic range you can achieve usually. So when you want to display an image on the screen, you need to work with 8-bit images typically. But when you want to run some machine vision algorithm, you don't want to display something, you want to process the data, you can work with more than 8 bits per pixel. But still, monochrome image, one information, one value per pixel. Now when you talk about color sensors, in that case, each pixel is typically encoded not with one, but with 3 values. These values correspond to the red, green, and blue channel. And if you zoom in into a screen, this screen, for example, if you look very closely, at each pixel you will see 3 LEDs. One is green, one is red, one is blue. And the screen at the pixel level will adjust the intensity of each pixel, of each color channel to restitute the color that is encoded at the pixel level. So once again, it is typical to encode a color image with 3 times 8-bit information, but you can also work with 10 bits, 12 bits. You will not be able to display this information on the screen, but for image processing, that's enough. Now what's interesting to understand is that each pixel is encoded with 3 values, so a color image contains 3D information. Each pixel contains 3D information. Only this 3D information is color information. And when we talk about a 3D camera, usually we are not talking about a color information, we are talking about depth information. We want to localize a pixel, an object in space. So the use case that we want to address is, most of the case, robot guidance. So it can be an industrial robot where you want to localize a part in space so that the robot can pick the part and place it somewhere else, pick and place application. Or it can be for navigation, autonomous robots. This is called an autonomous mobile robot, and they use 3D cameras to navigate, okay, in space. So this is the main use cases that we address with 3D cameras. That actually 3D camera is not a very good name. We should call them depth camera because they compute depth information. So what kind of data you get out of a depth camera? Actually, there are two kinds of data you can get. You can have a depth map that is a 2D image, but each pixel is encoded with 3 values. It's not the red, green, blue values anymore. It is the X, Y, Z values in millimeters that correspond to the position of the point imaged by the pixel in space. So each pixel will contain 3 values, X, Y, Z position, typically in millimeters. All of that is according to a coordinate system. In that case, the origin of my coordinate system is on the upper left of my bin, in that example. In most of the use case, most of the camera manufacturer will offer you the position to change the coordinate system. That's quite easy. Okay? So this is a way to provide 3D information as an image. So it's a 2D image, but each pixel is encoded with 3 values. Another way to take a look at 3D data is via a point cloud. I cannot show you right now. I don't have my computer. But you can create what we call a point cloud, and then you can rotate around the point cloud with a specific software. But same kind of information at the end. Now, question is, what kind of technologies you have available when you want to create 3D data, when we want to acquire 3D information? You have many, many different technologies. I will focus on 2 of them. Time of flight, stereo vision. I will try to introduce you to the technology so that you understand basically what the technology is about. I will not talk about the other kind of technologies that you find because this is not my expertise and because I only have 10 minutes left. It's a little amount of time to make an engineering presentation. So time of flight and stereo vision, I would start with the time of flight technology. So let me explain to you the base principle behind this technology. If you consider these 2 points, and one is your home and one is your office, and you know that you travel at a given speed from your home to your office. You know the speeds that you are going to, and you know how much time it takes for you to go from your home to your office. Can you compute the distance? Yes, you can. You do it on a daily basis. Okay? Now let's consider exactly the 2 same points, but one is a light source and one is a scene. The light beams emitted by the light source will reach the scene. It will be reflected by the scene and come back to the sensor. But I know the speed of light. If I have a timer to record how much time it takes for light to go from the light source to the scene and come back to the sensor, I can compute the distance from the light source to the scene. So that's the base principle of time-of-flight technology, and we will try to apply it to a camera so you understand how it works. So you have a scene, and you have a time-of-flight sensor. It's a specific kind of sensor, very, very similar to a conventional CMOS sensor, but yet it's a specific time-of-flight sensor. It's made of pixels. It works with a lens. Looks very similar to a conventional sensor. But it's not only about the sensor, it's also about the light source that you have around the sensor. And how does it work? And you have a timer that will record the time it takes for the light beams emitted by the light source to reach the scene and come back. How does it work? You will flash some lights, and the light beams emitted by the light source will be reflected by the scene and come back to the sensor. And for each pixel, you will somehow record how much time it took for the light beam to go from the source to the scene and back to the pixel. And based on this information, you will be able to compute depth information. What is the distance from the pixel to the point that was reached by the light beam? This is called direct time-of-flight technology. most of the cameras that you see in this show using time-of-flight technology, they do not use direct time-of-flight technology because actually there is no such thing as a timer that can record the time it takes for a light beam to go to one place and come back. That will be pretty hard to achieve. So what we do usually is indirect time-of-flight technology. We don't pulse a single time the light beams. We pulse them frequently at a given frequency. And what the camera will do, or what the sensor will do, so we pulse the light at a given frequency. These light beams will reach to the scene and come back to the sensor. And what we will do is we will take a look at the phase shift between the emitted and the reflected light beams. That is basically the idea. And by looking at this phase shift, it's exactly the same as direct time-of-flight. We are able to compute depth information. Okay? Some things that you may notice already, what happens if the light beams emitted at a given frequency, if they overlap perfectly with the light beams reflected by the scene. If my scene is too much further away from my light source, I will reach a point where the emitted and reflected scene waves will overlap one-to-one. And in that case, you will compute improper depth information. So that's something important to keep in mind when you work with time-of-flight technology. As a camera manufacturer, we provide you the opportunity to modulate this frequency, and depending on your working range, you will maximize data accuracy, depth accuracy, up to a certain point, or you can modulate the frequency of the light beams to work at the long range, but you will lower the accuracy that you can reach. Okay? So there's always a trade-off. So that is the principle of indirect time-of-flight technology, and I will compare it with another technology that we offer at IDS that is called active stereo vision. So the principle is absolutely not the same. The principle of stereo vision is the same as the human eyes. As a human, when you look at a point, the point will create an image in both of your retinas, and both retinas have a contains 2D images. So you create two 2D images on both of your eyes, both of your retinas, and your brain, based on these two images, will compute depth information. This is why we say that if you close one eye and try to reach your fingers, you will not be so successful. You will have improper depth information because you lose the stereo vision. When we apply this kind of methodology to a camera, it's not so different. It's called a stereo vision system. In that case, the N-Sensor C from IDS and Optonic. You have a point that you're looking out. This point will be imaged in both sensors of your stereo vision system. The camera does not have a brain, but it is connected to a computer. And on the computer, the driver of the camera, based on these two images, will compute the depth information for that point. The distance from both sensors of the stereo vision system is called the baseline, and it is a very important factor when you want to maximize the data accuracy, especially when you work in the long range. So usually you can keep in mind that the bigger is the system, the higher will be the data accuracy. And this is one of the limitations of stereo vision. If you want high accuracy in the long range, the device you will use will be huge. Okay? So huge footprint. And the angle between the two sensors is called the divergence angle. You can choose to have a very narrow field of view. In that case, you will have depth information with a high density of points per unit of volume. Or you can choose to have a very wide field of view, which is good because you have a wide field of view. But of course, if you have the same sensors of the same resolution, you will lower the spatial resolution that you can get. You have less points per unit of volume. So now this stereo vision system will acquire two 2D images and send them to the computer. And the computer is responsible to compute depth information. I will try to explain to you a little bit how it works. So the stereo vision system will acquire the same scene from different points of view. And the driver of the camera on the computer will go through each pixel of the right image and try to find the corresponding pixel on the left image. If this algorithm succeeds, I will compute proper depth information. If it does not succeed, I will not compute proper depth information. That's a limitation of stereo vision technology. So there is a matching algorithm into the driver of the camera, and this matching algorithm goes through each pixel of the right image. And when I have local contrast on my image, let's say on the drawing of the right image, I have a pixel that is black, pixel on the top is white, pixel on the bottom is gray. Can I find the equivalent pixel on the left image? Yes, I can, because each pixel is very different to the other. The problem that you have is with homogeneous areas. For example, in the background, you have a pixel that is white, surrounded by pixels that are white. Can you find corresponding pixels on the left image? No, you can't, because you have so many candidates, so the algorithm fails. So that is a limitation of stereo vision technology. It does not work well on homogeneous surfaces. What we do at IDS is we add an additional element, which is called a pattern projector. It is just there to add some texture to the scene, to make the stereo matching algorithm more successful. So if I use exactly the same example as before, I have the same scene acquired from different points of view, but now I have the texture that is projected by my pattern projector, and my algorithm will go through each pixel of the right image, try to find the corresponding pixel on the left image. Each pixel taken together with its neighborhoods is very unique, so my matching algorithm will have more chance of success. And I will compute a more complete depth map. Okay? Still keep in mind, you have some shadow areas that are not located on the same place from the left and right point of view. And that is still a limitation of the active stereo vision technologies. You do not compute depth informations for parts where you have shadows visible from the left and right point of view. Which comes to the last slide. How do you choose between time of flight and stereo vision technology? Time of flight has a small footprint. You understand with stereo vision, so it's a small camera because you have a single sensor plus the light source. With stereo vision, if you want to achieve high accuracy, especially in the long range, you need to have a wide baseline, which means a big product. So footprint. Price-wise, when you talk about active stereo vision, you talk about 2 sensors plus a pattern projector. When you talk about time-of-flight cameras, you need 1 time-of-flight sensor, a few LEDs, and that's most of it. So the price of the time-of-flight camera will be cheaper than the active stereo vision. Resolution. When we make a time-of-flight camera, we are limited by the resolution that the sensor manufacturer can provide to us. Today at IDS, we showcase a camera with 1.2 megapixel resolution. It is the best you can have with time-of-flight. With active stereo vision cameras, we provide up to 5 megapixel sensors. And if you have the need for 40 megapixel sensors, we can make it. That's easy to do because we use conventional sensors. The impact of ambient light is pretty important, especially with time-of-flight. That's always true with stereo vision, but this is something you want to consider because the camera can get confused by the light beams that are emitted by the ambient light and reflected to the sensor. The operating range of the time-of-flight camera, you are limited by the power that can be provided by the light source that comes around the sensor. And the acquisition speed, when you talk about the stereo vision system, you have to send 2 images from the stereo vision system to the computer. It will consume a lot of bandwidth. When you use a time-of-flight camera, you just have a single image coming out of the sensor to send to the computer. So usually, acquisition speed is better with time-of-flight technology. And now comes to the end of my time. I think you understand why I only compare 2 technologies and not 5 or 6, because 20 minutes is not enough.